Hello students, in this class we will extend our discussion on games and we will try to understand the games without saddle point, as well as we will learn the principles of dominance in game theory. First of all, two-person zero-sum game without saddle point. So for any 2 cross 2 two-person zero-sum game without saddle point, having payoff matrix for player A as player A having strategies A1 and A2, then player B is also having strategies B1 and B2. Okay, so this is the payoff matrix to player A, A11, A12, A21, A22. These are the elements of this payoff elements of this matrix. The optimal mix strategies and the value of the game are given by optimal mix strategy to player A. It is denoted by S subscript A and is equal to just putting inside the brackets, and above are pure strategies. Okay, A1, A2. So let this player A chooses strategy A1 with probability P1. These are probabilities. And A2 chooses with probability P2. And sum of P1 and P2 is 1. Where P1 is given by this expression A22 minus A21 divided by A11 plus A22 minus of bracket A12 plus A21, and P2 is equal to 1 minus P1. Similarly, optimal mix strategy to player B is given by Q1, this one SB. SB is equal to B1, B2. He chooses that he chooses the strategy B1 with probability Q1 and B2 with probability Q2, where Q1 is given by this expression A22 minus A12 divided by A11 plus A22 minus of A12 plus A21, and the value of the game denoted by V is given by this expression A11 A22 minus A12 A21 divided by this. So you can note that the denominator is same in all the three cases, whether you found Q1, P1 or you found Q1 and V. Okay. Now we will try to see whether these are the values or not. So we will try to prove it. Let P1 and P2, where P2 is equal to 1 minus P1, be the probabilities of selecting strategies A1 and A2 by player A, and Q2 and Q1 and Q2 be the probabilities of selecting the strategies B1 and B2 by player B. So we are talking now about mixed strategies. Okay, so then the expected value of the game to player A is given by this. How is this? Because A1 payoff corresponds to the selection of strategies A1 by player A and B1 by player B. If you see that payoff matrix, and player A selects strategy A1 with probability P1, whereas player B selects strategy B1 with probability Q1. So these probabilities into the value, okay, payoff value, okay, and this gives me expected payoff, and I have to take into account all the payoffs, okay, that are possible. So if the payoff is A21, then he selects the strategy A2, player A selects the strategy A2 with probability P2, and player B selects the strategy B1 with probability Q1. So similarly, I have written all this by simply using the definition of expectation. Okay, so all these possibilities are written and that's summed up. Okay, so this gives me the expected payoff to player A when both the players play their strategies with respective probabilities. Now this can further be written as P1 Q1 A11 plus P2. P2 is 1 minus P1 Q1 A21. So simply what I have done, I have replaced this Q2 and P2 simply by 1 minus Q1 and 1 minus P1, so that this expression remains only in the form of P1 and Q1. Now we have to find out the optimal values of P1 and Q1. Okay, we need to find the optimum strategies. So we need to have the optimum values of P1 and Q1. So for that we use differential calculus, and what we do, we differentiate E P1 Q1, this function of P1 and Q1 partially with respect to P1 and Q1. So once, if I differentiate this with respect to P1, I get this one. How do I get? If you see here, okay. So differentiate this, okay, only with respect to P1. So differentiation of P1 with respect to P1 is 1, and you are left with Q1 A1. Because we are doing it partially, so we are keeping the Q1 as constant. So yeah, so now you are left only with Q1 A11. Similarly from here, if you see, so P1 is here only, so differentiation of 1 minus P1 with respect to P1 is minus 1, because differentiation of 1 is 0 and minus sign remaining as it is, and derivative of P1 with respect to P1 is 1. So minus of Q1 A21. So it's very simple differentiation. You can try it out and you can see these are the values. Similarly here, only 1 minus Q1 A1 to left, and all this from here also. And similarly you find out partial derivative of EPQ with respect to Q1. So if we do it here, so with respect to Q1 I am left with P1 A11 and all other values as discussed earlier in case of equation 1. So we get these two equations, equation 1 and equation 2. Now for maximum or minima, set these derivatives equal to 0. So I am putting this equal to 0 as well as this equal to 0. So it means that now the right hand side values would be equal to 0. So that we are going to do now. So we get from 1 this right hand side value equal to 0, and now we do certain arrangements so that we can find out the value of Q1. So just taking the terms involving Q1 together, so Q1 here and this Q1 also here, and Q1 outside, inside this is left. Similarly from here, if we just expand it, we see this, and this is, these are to underline, these two terms involve Q1, so we can take all this common, Q1 common from all these terms. We are left with this and plus this and minus this. So if we take these two terms other side, so A22 minus A12 and divide by this multiple of Q1, that is this one. So A11 plus A122 minus A12 plus A21. So this is how we can find out the value of Q1. Okay. Similarly, we can find out the value of P1. So from equation 2, if we do the same kind of procedure, okay, we take all the values involving P1 one side and take P1 common, and then take the multiple of P1 to other side, and we are left with this expression. So this is the value of P1. Once you find P1, you can find out P2, because P2 is 1 minus P1, and similarly we can find the value of Q2 because Q2 is equal to 1 minus Q1. Okay. Coming next, the value of the game EP1Q1. It is, as it was earlier, it was like this. Okay, this was the value. Now after substituting the values of P1 and Q1 in this expression and solving further, we get V value of the game, E P1 expected value of the game, V E P1 Q1 is equal to this one. So denominator is same in all these cases, you get this one. Okay, so yeah, this is the value of the game. So we learned how to solve 2 cross 2 game without saddle point and how to obtain the optimal mix strategies. Next topic is principle of dominance in game theory. So what happens sometimes, the saddle point is not possible and the game is quite big in terms of its payoff matrix, and then how to solve in that cases, the inferior strategies are dropped or eliminated from the payoff matrix. So there are certain principles which we can use to reduce the size of this payoff matrix. So rule number 1 is if all the elements of a row, say kth row, are less than or equal to the corresponding elements of any other row, say rth, then kth row is dominated by rth row. The dominated row, that is kth row, may be deleted. Number 2, if all the elements of a column, say kth, are greater than or equal to the corresponding elements of any other column, say rth, then kth column is dominated by rth column. Thus this dominated column, that is kth column, may be deleted because the strategy corresponding to this kth column is inferior one, as it is producing a lot of loss to player B. Similarly, we can argue that if all the elements of a row in case of principal 1 are less than or equal to the corresponding elements on another row, so in this case also the particular strategy whose elements are less than the elements of any other row, that strategy which is dominated, that produces very less amount or less payoff to player A, and that's why the player A should not choose that inferior strategy. Okay, and thus that row or that particular strategy can be deleted. The third one is a given strategy can also be said to be dominated if it is inferior to an average of 2 or more other strategies. The row or column corresponding to dominated strategy may be deleted. Okay, so sometime it happens that you are not able to find that all the elements of a particular row are less than equal to all the elements of any other row, or similar thing happens with the columns. In those cases you can search for the average of any two rows or any two columns, and then again we can apply the same kind of principles like 1 and 2, that if the average of two or more strategies uh, dominates some row or some column, then that row or particular column may be deleted. And now coming to the next, that is an example based on dominance principles. So let us take this. Two firms are competing for business under the condition that one firm's gain is the other firm's loss. Firm A's payoff matrix is given below. Suggest the optimal strategies for the two firms and find the value of the game or net outcome. Okay, now coming to this is the payoff matrix. Player A this side, player B this side. These are the strategies. No advertising, and it is denoted by A1 symbol. Similarly, medium advertising, A2, heavy advertising, A3. And similar strategies are with player B also, denoted by B1, B2, B3. And this is the payoff matrix and payoff element. So if we see that maximin here is 12 and minimax is value is 14. Since this maximum value is not equal to minimax value, this game has no saddle point. So in such a case, if we reduce it, that is, it will have now the it is a game with mixed strategies, and we will solve it with the help of mixed strategies and without saddle point game. So we need to reduce it. We have learned a procedure to solve 2x2 games without saddle point, so we can use that procedure. But before that, we have to reduce it to 2x2 game, and for that we use principles of dominance. So we can see from here this first row elements 10, 5, minus 2, all these are less than the second row elements 13, 12, and 15. So it means that the strategy A1 is inferior to strategy A2 because it is always producing less output than the strategy A2. Okay, so accordingly this can be deleted. So if you see this, I've written here all the elements of first row are less than the corresponding elements of second row. Therefore, first row is dominated and hence deleted. Therefore, the reduced payoff matrix is like this: player A, player B, A1, A2, A3, B1, B2, B3. So these are the values from the original matrix. Only A1 is deleted. Similarly, if we see column wise here, then 13 is greater than 12, 16 is greater than 14. So if we see that the elements of first column corresponding to strategy B1 are higher than the elements of strategy B2, okay, that is 12 and 14. Okay, so this means that this strategy is leading to more loss to player B as compared to strategy B2, and hence this is dominated by B2. So we can remove this strategy B1. So all this is done. I have written the same thing here, and thus we are left with a reduced matrix like this: A2, A3, B2, B3. Now this is 2x2. Okay, again if we see from here that it is not having any saddle point, because row minimum, if you see, it is 12 and 10, and maximum of those is 12. Similarly, from column wise, if we see column maximum 14, 15, and if we take minimum of 14, 15, that is 14. So 14 is not equal to 12, and hence it is a game, again game without saddle point. So let SA like this: A1, A2, A3, okay, P1, P2, P3, these are probabilities, and SB, B1, B2, B3, Q1, Q2, Q3 probabilities. Be the optimum mix of strategies to players A and B respectively. Okay, and we know that the optimal strategies for a 2x2 2-person zero sum game without saddle point are this. We have just studied earlier, a bit earlier in earlier slides. So the value of P1 we know this, and the value of Q1 we know this. But here, instead of P1 and Q1, we will talk about P2 and Q2, because the corresponding strategy names are A2 and A3 and B2, B3. If you see this, just go through A2, A3 and B2, B3. Okay, and so here this corresponding probability is P2, corresponding probability is P3, and here Q2 and Q3. So the formula remaining the same, but here instead of P1 I'll write P2 and here Q2. So yeah, so the value of the game is given by this expression. So P2, the same thing is there, same formula is used, like A22 minus A21 upon all this, and these elements are here, A22, A11, A12, A21, A22. Okay, so these are elements are put over here. So I get 4 upon 7 and P3 1 minus P2, that is 3 upon 7. Similarly, we can find Q2 and it comes out to be 5 upon 7. This minus sign cancels like this. Okay, so then Q3 is 2 upon 7. Okay, and the value of the game now would be, just put the values from that 2 cross 2 matrix corresponding elements, and it is 90 upon 7. Hence we have solved this game by using the principle of dominance, and the optimal strategy is to player A and B are just given by this, as C is equal to A0, A2 4 by 7, A3 3 by 7, means he should not choose probability A as this strategy A1 because its probability is 0, came out to be 0, and he should choose the strategy A2 with probabilities 4 upon 7 and A3 with probability 3 upon 7. Similar interpretation can be given for the this one, optimal strategy, mixed strategy to player B. So these are the values, and the value of the game came out with this. Thank you very much.